All right, let's get started one last time this summer. Uh, yeah, so today's speaker is Katya. I'm guessing 90% of you at least know her, but I'll introduce her nonetheless. So Katya Kudashkina, she's a PhD candidate at the University of Guelph and Vector Institute, and she's been visiting us here for about 2 years now. So yeah, Katya, take it away.
Thank you, Abhishek. Yes, I was fortunate to make my second home the RLAI lab and Amii, and it's always an honor to give a talk here. And so I'm also fortunate to work with these folks that you see on the slide. And today I'd like to talk about our work in progress that we are all baking together, and that is about model-based reinforcement learning and planning with expectation models. And for those who have been to these tea time talks since the beginning, at the beginning of this summer, Rich gave a talk on functional approximations and the importance of it. And for those who have seen that talk, I'd like to keep in mind, so Rich talked a lot about the grand focus of looking for a better approximate answer rather than solving a bigger problem exactly. And I'd like to keep that in mind throughout this talk because we will be talking about the functional approximation here. And for many of you, it is not news that functional approximation is essential in model-based reinforcement learning methods, and especially in partially observable environment, partially observable MDPs. And it doesn't mean that we're saying this is the only places that it's important. It can be used in normal MDPs as well, but this is our focus for the purpose of this talk. And just as a reminder, in model-based RL methods, what we want to do is we want to train this fully intelligent agent that is able to learn. So we have this world, but we really want to learn some kind of model of the world. And we want to use that model flexibly and efficiently to plan the agent's behavior further. And allow me to introduce a little bit of notation so that we all could talk about the things on the same page. And for those who are familiar with the second edition of Rich Sutton's book, that's the notation I'll be using going forward. So let's start with the classic MDP. So in a classic MDP, we have our Markov state that is fully observable to our agent, and we have this true value function because the state is fully accessible. And so the value functions, V is stands for state value function here, and that gives the value of the state, and Q stands for the action value function that gives us the value of the state action pair, and pi is for the refers to the value functions under the policy pi, and star refers to the value functions under the optimal policy. And now, once we start with dealing with partially observable environments, partially observable MDPs, we can no longer talk about this Markov state. So we're losing this Markov state. And as a result, we can no longer talk about the true value functions. So now what we really want to talk about is this V hat, which is an approximate value functions parameterized by some weights that we learn, which is this W. And now consider a dynamic system that takes some sequence of actions and emits some observations. And the system would produce this stream of experience, which we call and refer to as this history H. And in this system, the agent would also receive some reward, which is this function of this observation. So now this history is what the agent interacting with the environment can actually know and observe. And now the state, what we want to call the state, is this compact version of this history, which is represented and has inputs such as the previous state, the previous actions, and the observations. So it's basically the agent's ongoing representation of the situation in this partial observable MDP, where the agent cannot really sense the complete state of the environment. And this process U, this function U, that how the new state is obtained, is implemented by some deterministic function that we call U here, and we refer to it as a state update. And some of you may have seen in the literature some other ideas such as belief state and predictive state representation. And what we're really saying is those are specific instances of the state update. So the state update function is really this umbrella for this other thing. So it's more general view on the state, on the agent state. And for the purpose of this talk, we also assuming that someone is giving us this U function, so it's given and it's known. So okay, so now given this state, this agent state that we're talking about, and the agent now can interact with the state and then can observe it and know it. And the state now, this is a compact version of this history and incorporate this most recent observation and the action. And now it's this ongoing representation. Okay, so now with this state, what we want to talk about is we can learn a model that given the stream of the experience. And this one model now is used further than to learn a policy and the value function. So this model will be parameterized by some parameter eta. And this model now is the way of generating trajectories. So it has these two parts. It has the rewards part and it has this transition parts. And because now this model is a way of generating these trajectories, now it can also form a well-defined MDP itself. And we refer to it as modeled MDP. So this is kind of an approximation of our wall environment MDP that we have. So it's not real MDP. And because it's not real MDP, it's also, again, this umbrella for what you may see in the literature as a belief MDP, which, again, is a particular instance of it. And now this view will allow us to talk about the expectations within this MDP and the value functions, and to differentiate them from the true value functions. We now call them this, we're giving them this tilde at the top to separate them from the true value function within the real environment MDP that we have. Okay, so, and from now here, we assume that we operate in continuous state space. And the assumption is partially because we can't really truly know if the state space is finite within this MDP. Okay, so now let's talk about planning. So the term planning used in reinforcement learning in several ways, and there are two very distinct approaches. And one approach is state space planning, and which entails the search through the states for the optimal policy. And I like to think about it that if you think that the states are really moleculars, and if we make compounds of those moleculars, then we could think about these compounds as a plans, and we could think about plan space planning that way. It's not one-to-one mapping, but it's just one way to think about it. And for the purpose of this talk, we are focusing on the state space planning. So we're looking at the search through the states, through states for an optimal policy, where we want to learn the model, simulate the experience with this model, and then using that simulated experience, compute the value functions, for example, by the backup operations, and then use that to improve the policy. And one simple way to look at the state space planning is an approximate value iteration. So, and for those who have seen that in the RL book, this is the not a new formula. So here it's an approximate value iteration, and all we changing here now, we have this tilde v for the parameterized state value function, parameterized by W, where W is this learned weights. And now you may also notice that the transition probability is now parameterized by eta because they come from the model, and the same with the reward. And we also changed the sum to this integral because we're talking about continuous state space. So now what we're going to do is we're really taking this formula and we're simply rewriting it as an update for the weights. So it's exactly the same thing. Now, so here we're proceeding, we're sweeping through the entire state space, and we updating the delta V, the approximate value of each state, based on the best model's one-step projections and the estimated value of the resulting states. And so to calculate, now what we're actually interested in is this integral. And to calculate this part, we have a different choice of different models in model-based methods and planning with function approximation. So let's look at the few possibilities. So the first possibility is when the model computes the probability of the next state as a result of the action taken by an agent. And we call them often distribution models. The output of this model is deterministic, so we also call them deterministic models here. And often these models are used with some special forms of Gaussians or Gaussian processes, which are these two works. And however, especially in reinforcement learning, because the environments are dynamic, as opposed to some static data sets as we may see in deep learning, then learning these distributions become more impractical than in classic deep learning. And the distributions become very large objects, and which require quite efficient ways to compute them. And the second possibility is to learn sample models where we still have to learn the distribution, but now we have to only produce a sample of the next state. And it's a little bit easier because the output now is more compact, so it's more computationally feasible. But the disadvantage of it that in planning, in order to achieve the outcome that we want and to get the representative state of the next state that we want, we may have to draw a few samples in order to see what happens next in the environment. So, and another alternative to this is expectation models. And those are the models that produce the expectation of the next state. And they have been quite an obvious choice in deterministic environments, which are these two works. And also, however, we often have to deal with stochastic environments. And Yi-Wan from our group, from our LAI group, has done some work, and they have an HK paper that shows the planning with expectation model in stochastic environments, and they show how planning with expectation models with linear value function can be equivalent to planning with distribution models in those settings. And this expectation model, so this particular two things is within our interest because they can be so much more efficient where you don't need to calculate all the full distributions, so they might be way more feasible in practice. So now let's just take this equation that you see in blue. And so I'm just rewriting it here. And now let's take the previous update that we saw. And what we are interested in our work is the control settings. And let's now consider the extension of planning. So we're taking this and we extended it to control settings. So we want to look at the action value functions now and see what the action value iteration will look like. So really what we're doing here, we're replacing this with max and we're using this action value functions. And now the question is this still the case? Is this equation, does this still hold? And so our hypothesis is that it really doesn't, and we cannot really plan this expectation, with action value functions using the expectation model. And so the reason is because the best action now depends on the specific state. And in other words, we can't plan an action using the expectation model because knowing average state is not really enough because it loses the flexibility of choosing different actions in each grounded state. So because the action now depends on the action really depends on the grounded state and not on the average state. So let's take a look at the example here, the counterexample that we call. And so imagine this MDP where we start with the start state and we have two actions going left and going right. And then we get into this next state with the equal probability. And then we have 4 different actions where we could either win or lose. But this MDP is quite boring. So imagine now that your agent is a magician and it has to go for a walk or not going for a walk, and it could meet a monster. And if it does go for a walk, then it could meet either a red monster or a blue monster. And because it's a magician, the agent is a magician, so it could use a different spell, and it has a blue spell for a blue monster that puts the monster to sleep, and red spell for the red monster that put the red monster to sleep. And if it uses the right spell for the right monster, meaning it takes the right action, then it gets +1. And if it doesn't, it gets -10. And if it doesn't go for a walk, then it gets 0. So the clear optimal policy now is to go for a walk and meet a monster. But now let's think that if you have an expectation model and we're taking a walk, and then you want to take the best action, so we want to do the max over all actions. But now if you have this expected state, then what are we actually going to get? well, any action would be bad, because what we're actually going to get is this average monster. And this average monster really now is the expected feature vector of this next state. And because we don't have the grounded state, we only have this average state. So now the expected state of these two monsters is equally likely. So now all actions are really bad, because we can't use this either of those actions on this monster. And the max doesn't help here, because if you don't do that, then the other option is don't go for a walk, and it's clearly not an optimal policy. So it's almost like you have to get to the state, see what monster is in there before you can commit to the action. But in reality, you don't get that. So the expectation model doesn't work here. And there is no good action. So this is our S prime here. This is our S. So the expectation model is not good here, because S prime giving you this next state, giving you an average. And in other words, our value function here has never been trained on this grounded state. And here we are losing an option of choosing this action as a function of this usual states, because we have only an average state. And this happens only in stochastic worlds. In deterministic environments, we wouldn't have this problem, because the expectation always would be the same. So basically, we cannot define action value function for this average state. And if we want to use expectation models, then what do we do? Well, then we're stuck with the state values. So, for example, methods like actor critic would be a solution here if we absolutely, by no means, have to use expectation models. So there are a couple of works that actually do use the action value functions with planning. So one is work by Rich, where we have this, he presents this dyna where essentially it shows eventually this good performance, but then it's really unclear. And this is done on the mountain car environment. And then there is another paper by Sorg and saying that where they learned this expectation model for each option in doing model-based planning. And the question is, can we make a statement that action value function don't work for planning, and then these two results are actually not quite applicable? But I think the bigger question is, the better statement is that we cannot learn the action value function and then act greedily with respect to it when using function approximation. So this problem really is not, it's not narrowed to, in particular, planning and expectation model. It's probably a bigger problem related to function approximation. And that is, so again, this is still an open question, and this is a work in progress at this point. And so what we're looking at now is we're looking at this particular question that I just raised, and we're looking at showing some empirical results with that. And we're looking at extending, so the Y1 results that I referred to earlier in this talk. So they show that planning with expectation model and its equivalent to planning with distribution models. So we looking to extend that also within this context of the agent state and the modeled MDP, and extend that particular statement. And then we're looking deeper into planning with linear and nonlinear value functions, whether it's state value functions or action value functions in particular. And some references for those who will be interested in those. And thank you very much for your attention. Thank you, Ashley.
So quick clarification question. So that was an interesting example. Could you shed some light on why in that example you would be able to plan with state values but not action values?
Why we would be able to plan with state values?
Yeah.
Because we don't have this problem. So for state values, I should have actually. Let me go back to this formula. 1 second. Let me go back to this particular case. Okay, yeah, that should be enough. So here, if you look here, Abhishek, so in this case, so when we're doing the planning with the state values, so what we're really doing is, it's like, think about it this way. We're querying here this next state, and then we add in the reward to it, right? So the reward part comes later. So it's like you look, let me try to explain it a little bit better. So you calculate in the current state and you query in this next state, and now only then you're looking at the reward at that state. And it's kind of, you're already doing this one step look ahead. But when you're doing the max of so here, when you're doing this max of the action value function, then all your information already has to be in the action value function to calculate what the result should be. So you already should contain all the information about the state and the action together, and that information together has to come with action value function. So it's almost like you have to get to the state first to know. You have to see the state to see to figure out which action you want to take. But when you get to that state and you see only the average state, and then you because you never seen if you haven't, think about it this way: if you have an option to train an action value function with a grounded state ahead of time, so if you could back it up, for example, then you wouldn't have this problem. But because you don't have a backup on the true action value function, then you can do it. So, and actually, let me make one more clarification. You may be able to plan this action value function, but maybe it needs to have some different algorithm. So you can't do this particular thing. Like maybe if there is a different algorithm for doing that, which we'll try to figure out as we, again, this is just work in progress, which we continue. Then maybe you can do the planning with action value function. But in this particular setup, you don't have the information to figure out which action is good. Does it make sense? Does it answer your question?
Yeah, kind of. Yeah, I'll think more about it. But yeah, thanks.
Okay.
I just wanted to chime in, like that explanation, like maybe another way of seeing it is that we're talking about linear models in both cases, V and Q. And expectation model, like the reason it works is because of linearity, right? If you have a linear function, then you can take the expectation of the features and then dot product with the weights. And that's the same as taking, and the problem is that when you take the max of a linear function, that's no longer a linear function. So in the V case, you just have a linear function. In the Q case, you have a max of a linear function over A, and that is not linear, and so you can't use expectation models anymore. But I have maybe another question about the example. Sort of, I'm just thinking sort of intuitively. So I guess. Yeah, so I guess the problem is that, like, let's say that you've got these two monster states, and each of them has some spell that works, right? Like it depends on which monster it is, but in both cases there is something that works, which means that the value function of both of those states is high, right? Like under some policy, right? There is some policy under which the value function is pi, the state value function. And so in principle, you should be able to back up that state value function to the previous state and get a high value for it. Because if both of the monsters have a high value, then the average monster also has a high value, right? And that's all that really matters. So yeah, I guess this is more of a comment, but like, and I'm not sure, like maybe this doesn't work when you have Q functions. I don't know. I have to think about it, but yeah.
Yeah, it's a good comment. Thank you, Roshan.
Sorry, I should also add that my comment only applies to like I'm not saying that an algorithm could find a good policy, right? Because how do you actually find that policy of doing the right thing for each monster? But assuming that you had some magical policy algorithm, then it's not the backup part that will sort of stop you, because the backup is just going to the average monster, you don't care. Both of them you have good policies.
Thank you.
Katya, could Can you hear?
Yes.
Can you clarify? Do the value function has to be linear, but do the models have to be linear?
Yeah, it's a fantastic question, Rich. I wish I knew the answer, but I think it's something that we actually need to clarify for ourselves, because these two works that I showed, they have linear models, right? And in Yi's work, it doesn't. So Yi's work has both linear and non-linear models, but he's using linear value functions. So I think we need to look at all the combinations actually and decompose for each case the statement.
So why would the model have to be linear? I can see the value function linearity requirement. I feel like, Rich, you asked the question because you have part of the answer. Do you want to elaborate?
No, that's part of the answer. Yeah,
I think Katya said it correctly, that the new work with Yi and Zahir, their paper, the expectation model, the model does not have to be linear, just the value function. Yeah.
Yeah, I think it goes a step ahead and says that linear models are not enough. It says that even if you have the best linear model, the fixed point is different from the TD fixed point, but with a nonlinear model, that's fine. So yeah, I think they relax even they don't even say you have to be restricted to linear models.
So I'm sorry, I'm being a little daft here. But what was the assumption that you would need to have linear models? Like you're saying that work shows that the value function needs to be linear and the model doesn't. But that's surprising because there's a result that shows you need to have linear models, I guess. Can you guys tell me what you're talking about? Like, is there some literature that says we need to have linear models?
So the earlier work used linear models, and then the latest work by Yi and Zahir, they use both linear and non-linear models. And they show that it doesn't matter if the model linear or non-linear, then as long as the value function is linear, then what they show that the planning with expectation models is equivalent to planning with distribution models, but the value function has to be linear, and the model doesn't matter in that case.
And I would agree with Martha that the argument for that we need nonlinear models hasn't really been made. I mean, I think it is a restriction, obviously. If you don't limit yourself to linear models, you could do either linear or nonlinear. And so it seems more powerful to have the possibility of nonlinear models, but it hasn't really been shown that you need them, given that you're going to have a linear value function. The requirement for a linear value function implies, for example, that your state representation is rich enough that you can represent a sufficiently varied set of value functions. And so once you've assumed that the state is so rich, then it's one could surmise that maybe linear models are enough. I think it hasn't really been shown or established or even argued that we need linear models. And it's quite there's one other result that I associate with Ron Parr and a bunch of co-authors wrote a paper about linear models and what you can do with them. And given that you've assumed a linear value function, and it's a result that suggests that maybe linear models are enough, but it's just suggestive. So it's kind of an open, interesting question.
Rich, wouldn't be that similar to the comment when we're talking. So you're saying if you have a rich representation of the state, and we have a linear model, wouldn't that be similar to something like when we have a very, so let's say, I'll talk a little bit from the deep learning perspective. When we have a very deep model, and then essentially we consider the first part is what's really forming the features, and then really we have this linear output as a last layer. And then in our case, like we have this first part is really represented. We call it that state.
I was answering the question with my mute on, but I wanted to agree that yes, it is. In both cases, you have the notion that the earlier layers of the network compute a representation, and then you're essentially linear in the last layer, and that applies to value functions, and it could also that line of argument could also apply to the model. So the model perhaps could be linear. It's really, I don't know. I think it's very clear that action models or that action value you can't plan as you described today as using an expectation model and action values. That's clear. But whether we need nonlinear models is not 100% clear. Yeah.
So I think your argument, Rich, was if you have expressive features, then linear models become very expressive. So then you don't need nonlinear, the expressivity of nonlinear models.
Possibly. Yeah.
It seems reasonable to assume that our features would let you predict the expected next features, the features in the next state, expected features in the next state. That seems like seems reasonable.
It does seem reasonable, but there's also reasons to be suspicious of linear models. And with linear models, it's easy to get explosions. You know, a model that predicts things will be infinite because it cycles around and it's linear and there's nothing to stop it, and you just go off to infinity.
Are you going to iterate the linear model?
Yeah, when you iterate the linear model, like theta goes to 2 theta, and then you have infinity.
I may have missed it, but Katya didn't talk about iterating the model. I'll say it again without echo. Katya, you didn't talk about iterating models, right? I mean, iterating models is a whole other kettle of fish.
I think we're a little bit far from iterating models, Marcia. I think there are so many questions that we still haven't answered. And I think we steps way behind from iterating models. So we need to decompose and make clear these first few questions that we have, and then we can talk about iterating models.
If you iterate a nonlinear model, then you fail for the same reason that the value function has to be linear. If you iterate a nonlinear expectation model, then you fail. And so, you know, if you're into the combination of nonlinear model, linear value function, then the only way to make that work is all your planning is single planning step. There are no iterations of the model. But there's no reason to feel bad about that, because if you do single planning steps and then, you know, single backups, short backups, and then you do many of them, you can still find arbitrarily long plans. You know, you can find the optimal policy. It's not a limitation. You don't need to iterate models in order to find the optimal policy. And it's not clear that it's advantageous. Iteration. Do we want to iterate or do we not? It's an open question.
I also wanted to say that we have to be precise by what we mean by do we need models, because there's two questions, right? Like given a model, how do you use it for planning? And then the second question is like, how do you actually learn the model, right? And to me, it seems that for the first question, which is, like if all you're doing with your model is sampling a linear value function, using it to sample or perform backups of a linear value function, then it doesn't matter, right? Like if that's the operation you're doing, then effectively, if you have an expectation model, it's doing the same thing. But the second question is like, if you're, how do you find a model, right? How do you learn a model, and how do you use a model for policy improvement, etc.? And I think that's more interesting, and I think that's what Rich meant when it's not clear whether linear models are enough or not.
So I'd just like to point out, Roshan, the equation that Katya gave for value iteration is using an expectation model to find the optimal policy. It is doing control.
Yeah, exactly. And that's what I meant. In that situation, we don't because we can see that if V happens to be linear, and if you're restricting ourselves to linear value functions, then in this equation, you could replace it with an expectation model that predicts the next feature given a state and action, and nothing would change. But it's beyond that, like you were saying, if you have rich features, then it might actually make sense to learn linear models. But if you don't, then etc. Right? So it's beyond this that those problems arise, not just for planning.
I don't think I got the argument fully. So I think you were explaining why Rich said that we don't need, it's not clear if we need linear models or no, it's not clear if we need nonlinear models or linear models are enough.
Yeah, I was just trying to clarify that as far as this, for example, you can think of what's on the screen right now as an algorithm, a planning algorithm that iterates value functions. And if those value functions happen to be linear, which means the algorithm is maintaining an explicit value function representation, which is linear, then there is no advantage to having a nonlinear P, because this whole expression can be computed with just linear expectation models. But there are going to be other parts to the reinforcement learning sort of big algorithm, right? There's going to be how do you learn the model, and how do you learn a representation, and so on. And that is where possibly there might be some advantages to having nonlinear models, but not in what's on the screen right now. There you don't need nonlinear models.
Rich, I think you're saying something. Rich, are you talking to us? If you are, then you.
So I didn't quite get your argument, Roshan. I mean, this equation works perfectly fine with a nonlinear model, and I don't see that as strongly interacting with this equation.
Right. I just meant that sort of in a bigger system, you're also going to have some sort of representation learning scheme, and you're also going to want to learn accurate models and so on. And those tasks might become easier if you allow for the possibility of nonlinear models, depending on what assumptions you're making about the environment.
Right. You don't need to have such good features, for example, because your model doesn't have to be linear in your features. I think Fatima has a question.
Yeah, I see the question from Fatima. By linear model, do we mean that the state update function is linear? No, Fatima, we could, the state update function doesn't have to be linear at all. But the model itself, so when we say linear, that's the model itself separate from the state update function.
In particular, the state update function is never, almost never going to be linear. It's where we stick all the nonlinear stuff. It goes into the state update.
Right.
I also wanted to sort of give some pointers to sort of the current theory literature on these topics. So Simon Du has a paper from last year, which got published at ICLR this year, which says is a good feature representation enough for something Markov reinforcement learning or something like that. And there has been a lot of work recently on people trying to have good end-to-end algorithms. And by end-to-end, I mean including exploration and actually like finding out how quickly do these algorithms converge and stuff like that. And currently, the state of the art seems to be this assumption called low Bellman rank. And low Bellman rank is basically that it is linear, right? That the model is like the actual world is linear. And that's a very strong assumption, and it's not yet clear whether that assumption is needed. So, like Rich was saying, it's still an open question whether you need that or not. But when you do have that assumption, what you get is that all value functions under all policies are going to be linear. So, if you have a model and then you come up with a value function under that model, there are two questions you can ask. The value function is going to depend on the policy, and you can ask, or you can assume that the value functions under all policies are linear, or you can assume that the value functions under the optimal policy is linear. So whether V star or V pi, right? And the low Bellman rank and linear MDP assumptions, they all give you that all value functions are linear, which is a very strong assumption. And so that also seems to be sort of something we don't yet know whether we need that assumption. It does seem like the current algorithms need that assumption, but it's not clear whether we can design better algorithms or not.
Thank you, Roshan.
A very dumb question, probably. Why do we even need models? Or do we need them? So I read this nice paper. They had this zero variance policy gradient update, but to actually implement that, they needed a model. And maybe models are faster in. So we discussed this in the RL2 class that there was a model and it worked well, but do we actually need models? Or why do we need them?
Well, in our case, let me go back to this slide. This is what we use them for, right? So we learn the models essentially to improve the policy. So the hypothesis is that we learn the dynamics of, or approximate dynamics of the environment that we could simulate the experience with, that we could use to plan for, and as a result to improve the policy. And so at least in my practice of using models, if you think about the number of inputs, number of samples, or the better the number of interactions with the environment, then when you do have the model, because you could use the simulated experience, you could improve the policy much faster. So the hypothesis is that models can help us to improve the policy sooner and more efficient, in other words. So to your question now, do we need the models? Well, if we have a better way of improving the policy without the models, sure, then we don't need the models. But do we know those ways?
One of my favorite ways to think about this question is imagine you could store all the data you've ever seen and you got to just do as many updates on that as you wanted, for example, and you're doing Q-learning. What would we gain from, in that situation, having a model?
Yeah, it's similar to when we have the experience replay, that right, we improving the learning, the speed of learning. So the model is along the same lines. So we're simulating that experience of the agent.
In such a case, model. Sorry.
Go ahead.
I think in such a case, models will lead to faster learning.
Yeah, so that's what we've been seeing so far, right? So in all, at least what I've seen in model-based cases, then you're learning, it allows us to learn the policy faster.
And
Can
this
I-
includes
Because we
the
can-
model
we can-
learning time as well. This includes the time for learning the model as well.
Yeah,
So learning the model plus the policy is faster than just learning the policy. That's the hypothesis, or that's what you have been observing.
so that's what we've been observing in our experiments.
That makes sense.
Can I say that this is also an artifact of our current algorithms? Because our current algorithms are so sample inefficient, just like value iteration and stuff like that. So whereas learning models is more like a supervised learning problem, and we have like more efficient algorithms for that.
Yeah.
But in the glorious future, we could have extremely efficient algorithms, sample efficient algorithms for learning policies directly. And in that glorious future, we might not need models, or they might help for other reasons, whatever, right? So there's going to be a difference between what is true in practice right now with the RL algorithms we have and what could be possible in the future. And I don't think it has been like definitively shown that you cannot have high sample efficiency algorithms. From what I know from the theory literature, like in some cases there are lower bounds for learning MDPs, and there are algorithms that match those lower bounds, which happen to be model free, right? So in some sense, you can already get as efficient as you can possibly be without using models. But of course, we don't know how to do that in practice in complicated situations. So for example, with function approximation. But that's more like we don't know yet rather than it's not possible.
Yeah, exactly. I agree with you fully. And there's also a question from Patrick: is it faster in terms of per unit of compute? Patrick, I don't actually know if it is because, and it may not be. I don't have an answer to this question. We actually wanted to investigate it with our experiments because there is a separate group at University of Toronto and Vector that is looking at those things in particular. So they're looking at the computation time, and they basically ready to take our experiments, and so they have a whole pipeline of computing that properly. So we don't know, but if we are really interested in that, there is a particular group that is focused on that, and they would be happy to experiment with anyone's algorithm to do that.
I think I have one point of view that why models might be important. I think it's because they provide a way to track, like they're important for tracking since we cannot represent the value function exactly. Models provide a way to get a better estimate for the current state and get away from a good estimate for all possible states.
Yeah, there is a comment from Joseph that the environment in the complex world, the environment will appear non-stationary, and in those cases, the models can be useful. Yeah, thank you, Joseph. Yeah, that is a definitely useful comment.
So that's an example of actually, I was going to say non-stationarity is one, like a reward changes somewhere in the environment. Your model can update quickly and you can propagate that quickly, but it's maybe harder to update in your value function. And storing all the data from the past is not going to solve your problem. So that's why I was saying, Shivam, that I kind of like thinking about the setting where imagine you could save all the data, because then it starts making you think about situations where that's insufficient. For example, right now we try to use models to improve learning on one problem where you still have the second order problem of learning the model first. I might argue that the model is not useful in that setting, except for one really specific way, which I'm not going to talk about right now.
I should also say that this is also a symptom of the sample inefficiency. Like the intuition we have that we can't update a value function quickly is because we just don't have algorithms that can update the value function quickly. And if we did have good sample efficient value function learning algorithms, then maybe they could also track non-stationarity. Right?
Yeah, that's true too.
But in some sense, one is easier to track than the other. Like one reward change is like this immediate thing, and a small change in reward can make the whole value function change. And just inherently, that's a harder thing to track, I think.
But yeah, I guess it depends on your algorithm, because for an algorithm, making a big change is not necessarily slower than making a small change. It's like, where do you get the data to make that change, right? Like computation time yeah, it's only our current gradient descent like algorithms where you have to wait a long time to make a big change because they kind of work in small steps. But that's because we are kind of using off-the-shelf gradient algorithms. And so maybe it's possible that we can come up with better algorithms that can actually produce big changes to value functions quickly.
That's possible. One such algorithm could be one that learns a model and then uses that model. I'm just joking.
Right.
I don't think that's a joke. I think that is the fact. Like you can't rule it out because you can always have a value function algorithm that is secretly using a model inside.
Exactly. Yeah.
Yeah.
I think that's the other reason models can be helpful is they give you sort of a different parametric model class that has this computation part built into it. And so it's hard to, it's possible that it's a more compact model class, or there's something useful about the types of functions we can learn when we include models inside those functions. That I have no idea if anyone has shown that's true though. Thanks, Katya.
Thank you, Martha.
All right, I guess we can wrap it up here. And if people want to talk some more, I'm posting the link to the Gather Town. And yeah, you can just hang out there for a while. And yeah, from next week onwards, I'll say, I guess the RLI meetings will start and we won't have any more tea time talks.
Thank you, Abhishek, and thank you everyone for your questions.
Yep, thanks Katya for the talk. Bye-bye.
Bye.